I was saying the principle, in more general terms, it stands for this starting amount, the initial amount. Amount. Okay. E comes from the continuous part that we looked at with that in the table. And R is the continuous rate of decay. It's the continuous decay slash growth, depending on it going up or down. How much is disappearing every single moment? What rate is it? And T is going to be what? Yeah, T is still time. Time in years. Okay, so T is time in years. All right. Before we do any problem, we need to figure out what this R is. We can use our half-life information to do that. Blake, how much material would you like to start with? 1,000. Okay. You get to pick whatever you want, because you just need whatever you start with. You're going to end up with half that amount. So it's kind of like I'm trying to prepare you for the first problem on your assignment with Fish before. It doesn't give you any amounts, but it talks about half of it. Right? It's a similar idea. So we're going to have 1,000. E to the R, well, we know after 5,730 years, we get half of what we had before. Well, that would mean you're left with 500. So then if we did, all right, so we have that. So I'm going to divide both sides by 1,000, which would mean 5/10 is equal to E. And I'm going to write it as 5,730 times R, just to make it easier to write. So now our variable we want to find is in the exponent. So we're going to rewrite it in logarithmic form. So I'm going to do log base E of 0.5 is 5,730 times R. What's log base E mean now? What's the abbreviation for that? ln, right? So if you see that already, you could start writing this as ln. You could skip the log base E. If it's not making sense to you, that ln means the same as log base E. Keep writing log base E. So then this part is ln. So we have R equals natural log of a half divided by 5,730. This is a number we're going to use quite a few times, okay, for multiple problems. I don't want to round it, because if I round it, and we're talking about going out 5,000 years or 10,000 years, rounding early is going to cause big errors. So what I'm going to do is store it in my calculator. Okay, so we have our, okay, so if we went to our calculator, we can type this in, and we can get it to store. You have a store button, STO, right above the on button. So if I put out of this, and we have natural log of 0.5 divided by 5,730. Okay. It gives us this number. Now, remember the E, the -4 would be the decimal point before place the button. If we hit the store button, we can cause our calculator to store this number. Okay. So we're going to go store, and let's see, we're calling it R, QR. So let's go alpha R. So now, if we, after we press enter, anytime we typed in R, it's going to correspond to this number. Yes, Cole?
I was wondering, like, it's fine if, like, the calculator I'm using, it just kind of rounds out right for you, doesn't do the E.
Okay, your calculator will show more decimal places. It's probably set up to float 8 or 9 places. But that's fine. We'll do the same. You could do the same thing. Selena, did you have a question? Were you raising your hand? No. Yes, Melissa. Not. Oh, okay. Okay, so then store. Okay, so type it in first, then do the store. So now we went back to the problem. All right, so we know what our R is. We've stored it. Ahead. And it says if an object starts with 6 grams, how many grams of carbon-14 will it have in 25,000? So we don't know how much we're going to have. Started with 6. It's carbon-14, so that's changing continuously. And we have our R times 25,000. And this is R. That's not very well. Stored. Computer's getting too old and can't handle it. Okay, but we can type this in. 6 times E exponent key, and if we just type in R, it brings up R for us. It puts that number in, times 25,000 close parentheses, so try that. Yes, hold it. You're right up front there, hold it. Okay, so let's see, Brett, did you get that? What did you get? 0.29. Okay. Now that would make sense because if you looked at this 25,000 is going to have 5,000 time year periods, right? So after 5,000 years, it should be about 3. Then after 10,000 years, it's going to be about 1.5. Then about 3/4. Then about 3/8. And then we have to go through 5 periods. I bet that number's close to this. Now it should be just a little bit more because it takes 5,730 years to get it half, not just 5,000. So it's the way you can use the half-life estimate. This is where carbon-14 dating is actually used. If you have a material, how old is it? Okay, so archaeologists discovered an artifact started with 10 grams of carbon-14, now it's 4 grams. How old is the object? Okay, so we're thinking of our A equals, because it's still carbon-14 dating, so it's continuously changing. Well, let's see. The 10 grams, is that how much we end with, start with, the R or the time? Start. Right, so we're going to put it in for the T. We end with 4. E, we figured out our R from before. We don't know the time. Okay, so we're going to get the E to the RT part by itself by dividing the size by 10. Giving us 0.4 equals E to the RT power. Alright, so then we have E to the RT. Oh, that's exponential form. We want to get a variable by itself, so let's write it in logarithmic form. So it's going to be log base E of 0.4 equal to R times T. Now I'm using R, but remember that was a number we found. So I have a number times T, we'll divide by that number. So we have T equals the log base E of 0.4 sense? Why would that answer be reasonable? What's half of 10? 5. So how long would it take to get down to 5? Right, 5,730 years. So it's going to take a little bit more than 5,730 years. If we went through 2 time periods, you'd be down to 2.5 grams. Well, you're not down to 2.5. 4 is between 2.5 and 4, or 2.5 and 5. So the answer should be between 5,730 and 10,460. For tomorrow, your assignment is to finish the 513C worksheet, and then also the 513D problems that are on the back of your notes.
Did you notice